Paris, May 24, 2000. On a spring afternoon in Paris, in a lecture hall a few streets from the Seine, a small group of people did something no one had quite done before. They put a price on the truth. The building was the Collège de France, an institution so old that Copernicus was still alive when it opened its doors. The audience was a mix of mathematicians and reporters, the mathematicians looking mildly puzzled to find reporters there at all. Outside, the chestnut trees were coming into leaf. Inside, two of the most respected mathematicians in the world stood up, one after the other, and read out a list. 7 problems, each one unsolved. Each one, from that day forward, worth $1 million. The money came from a man named Landon Clay, a Boston investor who had made a fortune in mutual funds and had spent a good deal of it on things he thought the world was neglecting. 2 years earlier, he had founded a small institute devoted entirely to mathematical research. Now he was doing something stranger than funding a laboratory. He was setting a bounty on ideas. The terms were unusual, and they tell you a great deal about what mathematics is. You could not submit your solution to the institute. There was no envelope to mail, no form to fill out, no committee waiting to receive your manuscript. Instead, you had to publish your proof in a serious mathematical journal, where strangers would take it apart line by line. Then you had to wait 2 years. If, after those 2 years, the mathematical world had read your argument and could find nothing wrong with it, if it had quietly become part of what everyone simply knew, only then would the institute consider paying you. Think about what that means. The prize was not awarded for a discovery. It was awarded for a discovery that had survived. In most fields, being right is something a panel decides. In mathematics, being right is something that the argument itself has to prove over and over to everyone who cares to check forever. The date was not an accident either. 100 years earlier, almost to the season, a German mathematician named David Hilbert had walked onto a stage in the same city, the Sorbonne, a 5-minute walk from where the Millennium meeting was held, and delivered a lecture that would shape the next 100 years of human thought. Hilbert was 38. He was not there to announce what mathematics had achieved. He was there to announce what it did not yet know. He listed the great unanswered questions of his time. 10 of them out loud, 23 in the printed version that followed. And then he said the thing that made the speech famous, that these problems could be solved. That in mathematics there is no ignorabimus, no we shall never know. 30 years later, at the end of his career, he put it more simply in a radio address that still survives as a scratchy recording. We must know. We will know. It worked. Hilbert's list became the century's agenda. Careers were built on single entries. Some problems fell within a few years, some took decades, some turned out to be badly posed, and a few produced answers so shocking they changed what mathematicians thought mathematics was. Young researchers picked a number off the list the way a climber picks a mountain. Which brings us to the strangest fact in this book, and the reason the Paris announcement in 2000 was not simply a nostalgic repeat performance. One problem is on both lists. It is Hilbert's 8th. It is also a Millennium Problem. It was first written down in 1859 in an 8-page paper by a shy German named Bernhard Riemann, who was writing about prime numbers and mentioned it almost in passing, as something he thought was probably true but had not managed to prove and did not want to spend more time on. It is still not proved. Not in Hilbert's century. Not in ours. As you read this, it has been open for more than 160 years, and thousands of published mathematical results begin with the words, assuming the Riemann hypothesis. Theorems built on a foundation nobody has been able to reach down and touch. The other 6 are no gentler. One of them asks whether every problem whose answer is easy to check is also secretly easy to solve, a question that sounds like a riddle and turns out to hold up modern banking, internet privacy, and possibly the value of human creativity. One asks whether the equations we use to model air over a wing and blood through an artery might, under the right conditions, break down and produce nonsense. One asks why the particles that hold the center of every atom together behave, as though they have weight when the theory says they shouldn't. One asks what shape the universe could be. 2 of them are so abstract that explaining them properly is itself a small work of translation, which is part of why you're holding this book. These are not puzzles. That distinction matters. A puzzle is difficulty invented for pleasure, and the world is fine either way. These 7 are load-bearing walls. They hold up bridges of reasoning that other people are already walking across. When mathematicians say a problem is deep, they mean that an answer would not just close a question. It would rearrange the furniture in rooms far away from where the question was asked. And the $1 million? Every mathematician in that Paris hall knew the money was, in one sense, a joke. Nobody solves a problem like this for money. You cannot buy a proof. There is no amount you could offer that would make the Riemann hypothesis easier. The people capable of attacking these questions are people who would attack them for nothing, and generally have been, for years, at some cost to their sleep and their families. But the Institute was explicit about why the number was so large. It was a megaphone. It was there so that ordinary people reading a newspaper over breakfast, people who last thought about mathematics in a classroom they were glad to leave, might learn something that mathematicians take for granted and nearly everyone else finds astonishing. Mathematics is not finished. Most of us are taught mathematics as a closed book. The rules exist. Someone worked them out long ago, presumably a man in a wig. Your job is to learn them, apply them correctly, and be graded on it. Almost nothing in that experience suggests that at this very moment, in offices and cafes and on long walks, thousands of people are pressing against the edge of the known and finding it will not give way. That edge is real, and it is closer than you think. You can walk right up to it in an afternoon. Some of these problems can be explained to a curious person in 20 minutes, which is what makes them so maddening and so beautiful. A question a child could ask that the entire human species cannot answer. Since that day in Paris, one of the 7 has fallen. It was solved a few years later by a Russian mathematician who did not publish it in a journal, did not apply for the prize, did not attend the ceremony, and when the $1 million was finally offered to him, said no. He also turned down the highest honor in mathematics, the Fields Medal. Then he stopped answering the door and stopped doing mathematics. And as far as anyone knows, he has never explained himself in a way that satisfied the people who wanted an explanation. His story is the end of this book, and it is not the story you would expect. It is not really about a man refusing money. It is about a person who took mathematics so seriously that a prize seemed beside the point, who looked at the world's most famous unanswered question, answered it, and then found that the answer was the only part he had ever wanted. 6 remain. They are sitting there right now. 7 pages of formal statements on a website written in a language most people cannot read, describing gaps in human understanding that money cannot close, that committees cannot vote shut. And that will yield only to somebody, someday, thinking of the right thing. Let's go look at them.